This is Geometry Chapter 2. We're on page 491. Now, I have taught you the word tangent. This is the same word, different meaning, right? We have words like that in our English vocabulary. All right, the tangent that I have taught you dealt with right triangles, and the tangent was a trig ratio where the tangent of any angle equals what over what?
Opposite over adjacent.
Opposite over adjacent. That is not this word. This word is related to a circle, or actually any curve, and this is a foundation for all of calculus. All right, a line is tangent to any curve when it intersects it at just one point. That's a line tangent to the circle. We can have curves, and if the line is just tangent to a curve, that's not a very pretty drawing. If it intersects it at one point, this is the foundation for calculus. That's what you're finding when you find the derivative. You're finding the slope of that line that intersects that curve at one point. Because the whole purpose of that is to find the rate of change over a very small interval on the x-axis. All right, so tangent lines are really to find what is the rate of change right there at that one point. All right, so look at the definition of tangent to a circle. And now you know lines can be tangent to any curve, not just circles. But if it's tangent to a circle, it's a line in the plane. It has to lie on the same plane of the circle that intersects the circle at exactly one point. This is not a line tangent to it. That is not. We're going to learn what that line is called, but that is not a line tangent to it. This is not a line tangent to it. What's this called? A chord. And that is actually called, it's called a secant. You're going to learn all this in this whole lesson. All right? But we're talking about one that intersects it at one point. There is something particular that happens that we can know if we have a line tangent to a curve. So I'm just going to redraw the circle and a line tangent to it. All right, we're going to say that line is tangent to the curve at that point. That is the point. If I have a radius, so the radius contains the center, right? And I draw a radius to that point of tangency, then I can know that this radius with the tangent line forms a right angle. So a line tangent to a circle, if a radius intersects the circle at that exact same point, then we have a right angle. Okay, this is useful particularly because we always want to draw right triangles. If I draw a line there, it makes a right triangle. So oftentimes I can use this information and trig to figure out the length of the radius because I have a right triangle. All right? All right, so look on page 492 and let's read the couple of theorems. They deal with this one fact, but the way that I see this on tests like the ACT is anytime I see it this way, or what we learned in the last lesson, if I know that that's perpendicular, then I know it bisects it. I can calculate the radius by drawing the hypotenuse of that right triangle. This is from the previous lesson, right? So I can solve for the length of the radius. Here, if I know any of any of the other information I can solve for the length of the radius. All right, so now let's read them. Theorem 59 on page 492. If a line is tangent to a circle, it is perpendicular to the radius drawn to the point of contact. What I just said, right? Yes. And if a line is perpendicular to the radius, so if I know they intersect at this point, I know they're perpendicular. If I know they're perpendicular, then I know they intersect, and that line is in fact tangent to the circle. Make sense? All right.